All right, so today we're going to talk about random variables. This is a section, or this is a chapter, where I'd like to have words with whoever decided the names of several of the things that we're going to do. Mostly for your sake. When you say random variable, it makes it sound like, oh, you can pick any letter you want. That's not what a random variable is in statistics. Okay? A random variable assumes any of several different numeric values as a result of some random event. So, for example, let's say that you had a deck of 52 cards. You called the ace 1 up through 10, called the jack 11, the queen 12, and the king 13. If you draw one at random, you're going to get one of those values from 1 to 13. Right? So that's a random variable. It's numeric now, not just it's a king or it's a whatever. It's always got to have a number associated with it. So we use capital letters for these, usually X, Y, or Z, which again, I'm like, are you freaking kidding me? My capital X's and my little x's look pretty much the same. Ditto for my Y's, ditto for my Z's. Okay? So I'm like, what fresh hell is this? So when you're doing capital X, try and make them look extra big or something. Put little, little horizontal bits at the top or something. I'm like, why? And the corresponding lowercase letter for particular values of these. Like, really? Okay. Now, if you can list all the possible outcomes, even if there are lots of them, and we'll see some of that a little bit later, it's called, if you want to be formal about it, a discrete random variable, meaning there's a limited number of values that you can have, as opposed to a continuous random variable would be like, if you on a number line, if you did everything between -3 and +2, there's an infinite number of numbers in between those two. You can't count how many different outcomes there are. That's a continuous random variable. So that's sort of like the same way math uses discrete versus continuous. A discrete graph, you almost never do them in math. We're almost always interested in a continuous one, but discrete ones are where you have, a bunch of dots that make some pattern or some kind. All right. The collection of all possible values of a random variable and the probability that they occur is called the probability model. Now, again, the word here drives me crazy. Usually a model is like the normal model, right? Where you have this whole thing that shows you the whole deal. This is sort of that way, but not quite. So it's not the word I would have used, but this is what happens when they don't invite me to the meetings. So at a state prison, there are 500 prisoners. 80 of the prisoners have no prior convictions. 265 have one prior conviction. 100 have 2 prior convictions, and 40 have 3 prior convictions, and 15 have 4 prior convictions. We're going to make a table showing the probability model, and this is what it looks like. We'll have a label, and I'm going to do prior convictions. X equals X.
Oh no. Oh no. That's Marty Law.
So the number of prior convictions, what are the possibilities?
8. Oh, wait.
That's the number of prisoners.
2. Yeah, none.
None.
Oh my goodness. Actually,
No prior convictions. That would be 0.
1,
1.
2, 3, 4. Guys, I caught on.
He doesn't know the next one.
Just ask me.
It's not always integers, but frequently it is. All right. Now here we want to put
There wasn't
the probability that x equals x. I'm going to try to say it that way every time I say little x. X.
whisper it.
Or I could just do deep voice, high voice. The probability that x equals x.
Thanks, Mr. Davis.
All right, so what's the probability that they have no prior convictions?
Well,
It's 80 over 500.
I was waiting.
1 is 265 over 500. 100 over 200 is the probability that they have 2 prior convictions. Only 40. Oh, sorry, 500. I don't know why I changed it to 200.
It's okay, Mr. Davis.
Let's set all the prisoners free. And then 40 over 500 and 15 over 500.
Alright, sounds good.
This table represents the probability model.
Yes, it does.
Now, another term that I think is potentially confusing is the expected value. Okay, the expected value of a random variable is found by taking each possible value multiplied by its probability and then finding the sum. Sounds horrible, but it's really not.
Okay.
The expected value gives a long run average. You can kind of think of it as a weighted average.
Is this like the large number? Wait,
The
what's
law of large
the
numbers.
law or the rule of large numbers? Is this kind of
No.
like that? No? Alright, never mind. Take it back.
The expected value, and this is the part that drives me crazy, the expected value is frequently, as in almost always, not a possible value.
Comforting. How? What?
That's the expected value.
Jackson's not happy.
It would,
Yes, it is.
see, I'm not happy with it either.
Yes, it is.
I think it would be better to simply call it the mean value.
Or the unexpected value, because it's never going to happen.
Well, I don't think that'd be a good name for
It's
it.
so what happens is if you took all the different things that could happen over a long period, and I guess in that it is somewhat like the rule of large numbers,
That's what I was thinking.
then this would be the average of all those numbers.
So.
So if I picked,
Super average.
yeah,
Don't
Let's
make
stick
it-
with the
don't make
Mr.
it
Davis
racist
side.
for
The
it.
so
The mean value.
I'd even be happy with the expected mean value.
Expected mean value. That's smart. That's smart.
Because the expected value makes you feel like, oh, sometimes this is going to happen. And frankly, it almost never happens.
Okay.
So let's take a look at this, the expected value here. So, and the thing is they use mu for it, which stands for mean, right? And the reason that it's a Greek letter here is because it's the population. So this is a parameter.
Oh goodness.
Population, parameter, statistic, sample.
A lot of layers here. Oh, that's true. Say the quote, Jackson.
So the expected value of x
Thank you for that.
is going to be equal to 0 times 80 over 500. So we're going to multiply the value of our variable times the probability.
Why is, oh, it's.
The value is 0, and the probability of getting to 0 is 80 out of 500 times. Plus 1 times 265 over 500. Plus 2 times 100 over 500. Plus 3 times 40 over 500.
I got this next one. Plus 4 times 15.
Stop, Shepard.
Yeah,
Thank you, Mr. Paul.
usually is.
And if you multiply all this together, you get 1.29.
Oh, because you're never going to get someone that has 1.29 prior convictions.
Exactly.
Oh, very good, Jax.
Now, in the long run, as a group, the average is they have 1.29 prior convictions. So that's why, again, that's why I feel like the mean or the average mean is a better way to say it, but it's the expected value. Now, why is it, I do understand part of why they call it expected value, because you can use that to help you figure out things. Like, for example, in your book, in the reading tonight, they talk about doing a selling insurance, and they figure out what is the expected profit from one particular insurance policy that's sold. And so that's how much you can expect on average to get. Insurance is a terrific thing to look at, because if I'm selling insurance, one of the things that I find really interesting is if I don't sell it to very many people, I may make a good amount of money, but I also may lose everything because I have to make one big payout to somebody. With insurance, much as with casinos, you want to have a lot of people. This is why really small insurance companies don't last very long. You have to get big, and you also don't want to specialize. We specialize in the Gulf Coast or whatever. Well, first hurricane that comes through, your company goes out of business. And your book makes a good point when they talk about it, in that if I'm the customer, I want the insurance company to make a profit. Because if they don't, they go out of business, and now what am I going to do?
Not insurance.
Right? So I want them to make a profit so they stay in business.
Still want to make that profit on you.
Yeah, and actually, you kind of don't mind that they make a profit on you, especially if it's a life insurance policy. If they make lots of money off of me, I'm perfectly happy with that. All right. So do you understand expected value then?
Yes.
How it's, I don't actually expect anyone to have that number of convictions, but in the long run, that's the average number of convictions amongst these prisoners.
You're the kind of guy to get exactly 1.2.
That was very funny.
Thanks,
That
Sean.
was very humorous.
Thank you.
This is why I think it frequently articles will talk about, the typical whatever has this many, the typical American household has 1.75 children. And I'm like,
Well.
it made it through, I don't know, how many months of pregnancy. And then we were like, well, we're just going to put it in the bottle now. I mean, it just seems wrong. What they really mean is, on average, they have that many. If you want to say typical, you can't say 1.75 children. Nobody has 1.75 children. Okay? At least not the way that anybody sane would count. Okay? All right. So,
Frankenstein's
Frankenstein's
creature, yeah.
all right. So variance and standard deviation for discrete random variable. This works just like it did when we did standard deviation and variance so long ago, except that what you're going to do is take whatever the value is of the variable minus the mean, just like we did before, and square it, but we're going to multiply that times the probability that that happens. That's the one thing that's different. And then the standard deviation is the square root of the variance. Right? We did that earlier this year also. So let's find the variance and the standard deviation for the number of prior convictions of the prisoners. Okay. So the variance of X is going to be, so for the first one, it'll be 0 minus 1.29 squared times the probability that that happens, which is 80 out of 500, plus 1 minus 1.29 squared times 265 over 500 plus 2 minus 1.29 squared times 100 out of 500 plus 3 minus 1.29 quantity squared times 40 over 500 plus 4 minus 1.29 squared times 15 out of 500.
What is this measuring?
Variance. And we take the square root of the variance to find the standard deviation. Yes, sir.
I actually,
You may.
I think you're past also.
Yeah.
Quiz stars and,
This comes out to be 0.6262696. The standard deviation of X is the square root of the variance.
This makes perfect sense.
One thing to notice on this is that because we're squaring this, it doesn't matter whether you put the 0 first or the 1.29 first. I mean, the formula says it one way, but if you reverse that, you're squaring it anyway. It doesn't matter. Okay, on to the back. So from our previous discussion on data, the adding and subtracting a constant shifts the mean, but doesn't change the variance, or therefore the standard deviation. The same is true for random variables, both discrete and continuous. Well, how does that work? Well, let's look at this example. If prisoners at a federal penitentiary have 2 or more convictions than those at the state prison, what are the expected value, the mean, and the standard deviation for the number of prior convictions? Well, the mean, yeah, is just going to be what we expected before, which was 1.26 plus 2. Everybody's got 2 more.
Woohoo! Oh, that's not good. That's not good. Convictions, right?
Yeah,
And that was X. Little X.
big X.
Oh, that's big X. No. X.
The variance of X stays the same, as does the standard deviation. So that's if we just add something. So if you're just adding, you're just taking all of the data and moving it, right? You're not changing how it's spread out in any way, are you? Now, on the other hand, in general, multiplying each value of a random variable by a constant multiplies the mean by that constant and the variance by the square of that constant, not the square root, the square. So note that since we take the square root of the variance to find the standard deviation, the new standard deviation is a times the original standard deviation because we're taking the square root of the variance. So, if the prisoners at a federal maximum security facility have twice as many prior convictions as those at the state prison, what is their mean, variance, and standard deviation? All right, so the mean, or the expected value of big X, is going to be twice as much as it was, so 2 times 1.29. So that's 4.58. The variance of X is going to be 2 squared times the old variance, 0.6262696, which is 2.505. And the standard deviation of big X then is going to be the square root of the variance. So that's the square root of 2 squared times 0.6262696, which is 2 times the square root of 0.6262696. So that's 2 times the old standard deviation. And the old standard deviation was what? 0.79137? So that's going to be 1.582. Where did I get that number from? It should be 2.58. I apologize.
It's okay,
I'm just gonna rage quit.
Please,
Just
please.
walk out,
Please do this shit.
pull a Mr. Catch.
You gotta coin that.
You go pack up your car.
Pull up Mr. Couch. Roll up the
I-
posters
Miss
outside.
Jones will have to take over your class.
Oh, please, bro. Mr. Bauer
So,
volunteers.
I did work with a guy once. He was a former engineer who had gotten old enough to where it was hard for him to find a job because there really is ageism, especially in engineering.
Yeah.
And so he decided, well, I'm smart. I can teach math. And and so he used to come down and ask me questions like, I'm having this problem in my class. And I would give him a suggestion, and he would always go, no, that's not it. What do I know? I've only been teaching at that point for almost 20 years, but no problem. Walt was his name. I don't remember his last name, but before, no, it wasn't Disney. He wasn't anywhere near that pleasant. But before Thanksgiving, we saw him leave on a Friday, and he was carrying his little potted plant, and I'm like, yeah, he's not coming back.
That's crazy. Couch left right before Thanksgiving. He just didn't make it to
I've never
Friday.
seen a trend.
It's that time of year. between Halloween and Thanksgiving. I just can't go on. All right.
But it gets worse.
So in general, the mean of the sum of two random variables is the sum of the means. So if you have the average of this random variable and the average of this other random variable, and you want what is the mean of the sum of those random variables, you just add them together. Okay? The mean of the differences is the differences of the mean. That doesn't get a whole lot more straightforward. Here's where it's not as straightforward. So if the random variables are independent, the variances of their sum or difference is always the sum of the variances. Doesn't matter whether you're subtracting or adding. You're going to add the variances. And the reason for that is the adding people get. The subtracting, they're like, well, why don't you subtract? Well, remember, variance is a measure of how much variance you have between things, right? Whether you're adding them or subtracting them, you're still going to get more variance if you add on another variable than you had with just one variable alone. Because you already have some variance, right? You already have some differences. And then when you subtract, we're going to have even more differences now. Okay? In the end, I kind of had to just go, okay, I'm going to memorize this. Honestly. Okay?
Write that down.
There are some, and I would actually suggest that you Google, why do variances add? And there are some very helpful videos on why they add. They're not all great, but I remember finding one where I went, okay, I believe that now.
Okay.
Should already show the video.
Who's on the couch podcast?
Oh.
We can talk about that next episode.
So also note,
You
We
missed
start
that
a
one.
podcast.
This is an episode.
here's what helped me. Variability increases whether you add or subtract the variables.
So,
Your variability is always increasing the more variables you add.
that makes sense, I think.
Yeah, more different things can happen now. Note this formula, that this is the formula used for variance and standard deviation if an event happens multiple times. So if an event happens multiple times, we'll add the variances together however many times. Okay? All right, so let's take a look at this one. The mean amount of time it takes a customer to check out from a local full-service grocery line is 4 minutes, with a standard deviation of 1.5 minutes. Find the mean wait time and the standard deviation if there are 3 people ahead of you in line. Okay, so the mean wait time is just going to be
Dropping the equation.
He doesn't spoil one.
so there's 3 people ahead of you in line, right? So for each of you, the mean wait time is 4 minutes. So the mean wait time is just 16 minutes. I think that's pretty straightforward. You know, maybe the second person takes a little longer, maybe the third person takes a little less, but on average, it should take you 16 minutes. All right, so then the variance,
How waiting that long? I don't need it to take that much.
and this is for just one customer, is going to be 1.5 squared.
That's big X, right?
That's big X.
X. Just gotta say for myself.
So that's 2.25. So then the variance of that X happening 4 times
those are big X's, right?
They are.
X, 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 X.
Is that necessary?
Yes, bro.
Sound like we're at a really bad rave and you're playing a techno music in the background. X, 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 X.
Mr. Davis
Is that from experience?
Mr. Davis standing outside the room.
Oh yeah,
waiting on
I
buckets.
spend lots of my time on the weekends going to raves.
And the whole time you're thinking how long it'll take you to get inside, right? 2.25 minutes.
He's running this calc right in the
Right now, live.
Pardon?
Is this where we get our problems from?
Yeah.
From going to raves and going, I wonder.
How long this line is.
Where do you talk?
The other stat teachers are obviously at the raves.
The stat raves.
Yeah, stat teachers don't get invited to events like that.
Don't say that, Mr. Davis.
It's true.
I would invite you, Mr. Davis.
They don't have to get
Yes.
invited because they're the ones.
They wouldn't go
Yes.
anyway.
Yes.
And the standard deviation is going to be the square root of 9 is 3 minutes.
Oh, okay.
Okay, so here's what I want you to remember on that is variances always add. You can't add the standard deviations though. You can only add the variances. You can't add the standard deviation 4 times. You've got to add the variance 4 times and then find the standard deviation. All right, so when two, gosh, let's not do the wave.
We toned it down a little bit. We toned it down.
I appreciate that. When two independent continuous random variables have normal models, okay, please stop.
Sorry.
So do their sum or difference. We will use this along with z-scores to find probabilities.
Jump scare.
Where's my hat?
All right,
They're all at the
so
rave.
yeah, you've forgotten all this stuff. This is good that this is coming up, but
Where's the X bar?
It's all coming back.
X bar, that's where you get drinks at the rave.
X bar.
Wow, guys.
All right, given the time it takes for a customer to check out in the previous example can be described by a normal model, what is the probability that you will have to wait 10 or more minutes if there are 2 people in the line ahead of you?
0.
Okay, so, and by wait on this one, I didn't make it very clear. Let's put wait until your checkout begins.
We had something going. X-bar.
All right, so we want the probability that capital X is greater than 10. Where we know what is the mean going to be?
9.
No.
16. No. 2.25. No.
Okay, stop.
I'll keep
There
going.
are 2 customers ahead of you, and what's their mean wait time?
4.
4 minutes each. So this is going to be 8.
You got there.
Good stuff. That was
You didn't.
So what is the standard deviation? Well, we know that the variance for x plus x is going to be 2.25 plus 2.25 is 4.5. So the standard deviation of x plus x is the square root of 4.5. And I don't have that written down. 2 point something. Two 2.12132. And here's a case where you get to use your calculator again.
Hey.
And actually, I'm going to leave it as a square root of 4.5 because we can just put it straight in that way.
Okay.
So, I'm going to go to, I want a normal distribution
Remember that?
where the mean was
8
8. And the standard deviation is,
square root of 4.5. Say 45. What? Did you say 45? No, you did.
and I want, read the question, you will have to wait more than 10 minutes.
So greater than 10.
So I got to go back over here and change this to greater than.
It's all gonna be
10.
Oh wait, I thought it was gonna be 10.
Sorry, hit the.
It's all good, Mr. Hicks. I trust.
So there's about a 17.3% chance that you'll have to wait more than 10 minutes. Now, to show your work for that, remember, you can do it this way. This is a normal distribution where the mean is 8 and the standard deviation is the square root of 4.5.
So
And we want the probability that this is greater than 10. And that came out to be, what was it, 17 point percent?
good number.
Any questions?
Questions for later.
Okay,